it was MLE, it was point estimation, so these are the things we have done, and we would like to do some more. Now what happens is, once we try to get hang of this test statistics and this stuffs like this, what we actually want is to understand the ideas behind these topics, right? So in statistics, what happens is, when you have a data set and you're trying to manipulate with it, you're trying to get some information about how the data set acts, how it works, or you maybe graph it. So let us say you have a data set x1, x2. Let me write it down. We have a data set x1 up to xn. Now in this data set, what we can do is, we can see that x1, x2 up to xn is a data set, and the properties described by this data set could be as follows. The mean is written like this with the x bar. It is called the sample mean because we believe that this data set x1 up to xn, if it is not the population, then it was taken from the population by some sampling method. Now there are a lot of sampling methods in existence: uniform sampling, random sampling, and then there is collective sampling and lots of others of them. Okay, cluster sampling. So a lot of types of sampling are there, and they were taken by any one of those methods or a completely new one maybe. But anyway, they are members of the population and they represent a sample of the population, right? Our target is to understand the features of the population given this sample. So firstly, the sample mean is this. Okay, this is the sample mean, and we also know the variance is let me first I have already defined you moments, but I'll just write it down again. The average, which is given like this average E of x, or the expectation of the data set, if the data set is continuous, maybe discrete here in this case, then it is basically equals to the sample mean, right? And this sample mean is the best estimator for the population mean. So if the population mean is mu, this means that expected value of x bar is simply equals to mu. Okay, now there are a few other things we should note, that we have studied this kind of things, and what we would like to understand is what is a z-score now. So we would like to understand z-score. So how is a z-score related and what is a z-score? So z-score comes from the z distribution. It is a standard normal distribution. So let me give you an example. Given x is a random variable following normal distribution with parameters mu and sigma square. Okay, find the z score for, okay, so we want to find the z score for some value, and we are not entirely sure how to do that, but if you are asked to find the z score for some x equals to k, then the z score for x equals to k would be k minus mu by sigma. This is the z score. So what it means is that the z score basically follows the normal distribution. Now how to find probabilities of certain things? So suppose we have to find probability of x less than equals to alpha. Okay, so if this is the case, then what we do is we see that we subtract by the mean on both sides first, then we divide by the standard deviation, now since x is now if x is basically directly normal variable, it's fine, but if x is just representative of a sample which has n entries in total, then what we do is this: we multiply it by root n on both sides, and same here. Now this x minus mu by sigma multiplied by root n, now let t equals to root n by sigma into x minus mu. We can show that t is standard normal, that is t goes from normal of 0 comma 1. So when this happens, what we see that therefore probability of x less than equals to alpha, this value would just be probability of t less than equals to root n times alpha minus mu by sigma, right? And for the standard normal variable, what the answer would just be minus infinity to root n of alpha minus mu by sigma 1 by root over 2 pi e to the power minus x square dx, or it can also be written as phi of root n into alpha minus mu by sigma, where this phi represents the standard normal CDF, where phi is this, right? Now the integration parts and all these things, the prerequisite for integrals would be embedded from my previous videos as well. You'll get that. But the question here remains that when phi and when we have the standard normal variable, we can easily find out, and this is essentially what we call the z-score. The values of the standard normal variable for different probabilities have already been listed out quite often, and what we can do is we can understand if this function really is required in order to understand all the different properties of any probability we ever get. And when the values are like large enough, or when the sample size is large enough, obviously, then every variable can be approximated into the standard normal variable distribution, and this is basically where the central limit theorem comes into play. So what is the CLT? Given a random sample Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, p-value, and much more. You can also find calculus-related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. And this you can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. When this happens, we can write. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel. This, or in other words, or what you can do is you can write like this: probability of x bar less than some t can be written as probability of z, where z is a standard normal variable, less than t minus mu by sigma square by actually sigma by root n, not sigma square. So let me correct this part. Sigma by root n. Right, and this only happens when you have limit n tends to infinity. So it basically becomes phi z of t minus mu by sigma by root n. So this is how the CLT works. So it can be for any distribution. It may be for a binomial distribution, it may be for a Poisson distribution. It wouldn't matter really, but it can be for any distribution. And the prerequisite for this variance and exponential stuff would be given at the end of the video as well, so you can check that out as well. So this is the CLT, and we will talk more about it and solve maybe after that, or maybe some problems at the end. But this is it for this one. So enjoy the prerequisite, maximum likelihood estimator and stuff like that. Anyway, so let's get started. So firstly, understand what is hypothesis testing. And in hypothesis testing, what we usually do is we try to understand what is the hypothesis, what is the null hypothesis. So there are two kinds of hypothesis. The null hypothesis is written as H naught, which is this, while the alternate hypothesis is written as H1. Okay, and what we can do is we can understand this from various examples, and we can understand that this kind of problems have a lot of ways to be acceptance. But obviously, first we are trying to understand how to handle this. So a null hypothesis is something which is given, and we would like to say some parts about it, some parts about the null hypothesis, where how we can handle, like let's say if the null hypothesis is theta greater than equal to 2, then the alternate hypothesis should be theta less than 2. So what happens is, if h naught belongs to the set A and h1 belongs to the set B, and if U is the universal set, then we must have A union B equals to U, while A intersection B equals to phi. This is what it should have, because the null and alternate hypotheses are basically reverses of each other, so they are complementary. Now, that being said, what we can now do is we can understand it from an example, and while also understand the various terms involved, like type 1 error, that we reject h naught when h naught is true. So type 1 error is defined as, when we define type 1 error as the event that we reject h naught when h naught is true, and we can find the probability of type 1 error, right? So it basically is this. Now, one more thing is level of significance or significance level, which is usually denoted by alpha. So we set a significance levels beforehand for our test, and we say that if okay. So well, obviously this is what we call as the type 1 error gets, so probability of type 1 error given theta, if it is less than equals to alpha, which is significance level, and this usually gives us that the test is significant and we should proceed with it. But if the probability is greater than that, then there are other ways to test that. Similarly, there is a type 2 error. So this is called type 2 error, and it means that we are going to accept h naught when in reality h naught is not true, which is h naught is false. So this is also a type of error, and it is called basically type 2 error, where, or we can also call it bit of theta. So there are various ways of doing that. So since it is usually denoted by beta, you can write beta of theta, where theta is the parameter of the test statistic. Now, So we are given this entire thing, and now we are going to understand each and every problem in a very similar way. So what we are going to do is we are going to do 3 more examples, and very typical and very nice examples actually. And what happens is, when we do these examples, we are going to need a lot of basic theory, and theory that we have studied in statistics and theory that we have just studied right now, which is basically the application of these things. So I'll give you a minute to understand this on your own, and then we can start. Now for the examples part. B for real numbers a and b. Okay, for real numbers a and b. Okay, so how do we do that? Well, obviously in that case also what we are trying to do is we are trying to substitute this thing ax plus b, because were it only sin x dx, it would have been easier, right? So let us name the integral as I, and let us substitute y equals to ax plus b. Now, as in the previous problem, what we are going to do is we are trying to differentiate both sides to find an expression for dy in terms of dx, right? So differentiating both sides, we get dy is equals to a into dx, because the constant b would disappear and a into x is into differentiation is just a, and we have an extra dx always, we, as I told you. So dy would be a dx, or in other words dx should be equal to dy by a. Okay, now this would turn our integration something like this. It would be sine of y, because ax plus b is y, and dx would be dy by a, and this would give you 1 by a sine y dy. Now we know the integration for sine y, it is just minus cos y, so the answer would be minus cos y by a plus c. And it's time to put back the variable which we substituted, which would give us cosine of ax plus b by a plus c, which is the answer for our integration. So as you see, like this kind of equations are this kind of integrals can be solved by using simple substitutions, but obviously there are harder ones. So let us try to find out another integral. Evaluate integral of 1 by 1 minus 2x dx. Now what does this resemble of? Firstly, because the simplest way we can evaluate an integral or to find out what to substitute is to find out the most recent or the closest integral which it resembles to. So as far as I can tell, this resembles to something like this, right? Whose integral we known as ln of x. So if we can somehow transform it in this form, that 1 by some variable and d of that variable, we can do that. An obvious way to do this is to substitute 1 minus 2x, and since it is linear, we substitute y equals to 1 minus 2x. Now y equals to 1 minus 2x would give us a pretty easy way to evaluate this integral, because when you differentiate both sides, what you get is dy equals to minus 2 dx, right? And this would give you dx equals to minus dy by 2. Using this I should be equal to 1 by 1 minus 2x is just 1 by y, and dx is just minus dy by 2, right? And so the constant minus 1 by 2 comes out, and we have 1 by y dy. Now this would give us minus 1 by 2 ln of y plus c, and it's time to put back what we have substituted, which gives us minus 1 by 2 ln of 1 minus 2x plus c. So you understand that we are in every problem, what we are trying to do is we are trying to reduce the integral by using some magical substitution, or rather a rational one once you try to get the hang of it, to reduce it to an elementary integral we know of, and then evaluate it directly, and then put back the value of the variable once it is out of the integration to get back our result. So this is what we call the method of substitution. We'll see a lot more examples in the coming sections, obviously. So the general version for this one would be, the general version for this type of integral is dx by ax plus b, and you can evaluate it. So let us name it as I. Substitute y equals to ax plus b. Now when we substitute y equals to ax plus b, we can have dy equals to a into dx, right? Then I should be equal to integral of dx is dy by a, so put a 1 by a outside, dy here, and this should be y. So this would give you 1 by a ln of y plus c, and if you put back the value, it would give you 1 by a ln of ax plus b plus c, which is the answer. Okay. Now next example what we can get is something like this. We can try and find out some of the basic theorems regarding this, like so this one is a tad harder, but what I'm going to teach you in this, in regard to this problem, would be something that you should remember in your way along. So this type of an integral is not something where you just magically find the substitution, but rather you literally look for something. So that something is determined by the following theorem. Theorem says that if you have f of gx into g prime x dx, this is the form of the integral, which as you can see is the chain rule, then this is equal, then this is basically equal to the integral of f of gx d of gx, or you can say this is equal to f of y dy, where y equals to gx. So you just need to integrate the function f. If the function f is integrable to you in an elementary form, you would be done, right? Okay. So what we are trying to find is, if we can find something, some function which is a function of something, and the derivative of that function is already given along with dx, we can directly substitute that function. Why? We can see why. So given integral is I equals to 2x into root over of 1 plus x square dx, and we can substitute y equals to 1 plus x square. Why are we doing that? Because see, I realize that the integral of 2x into root over 1 plus x square can be solved if we were to eliminate this root over 1 plus x square thing. So when I substituted y equals to 1 plus x square, I saw that the derivative of 1 plus x square is just 2x, which is given along with dx. So 2x dx would be substituted into a single dy, which is what we wanted, which is basically the form of this function, right? So the derivative of 1 plus x square is already given outside. So when we do dy, what we get is 2x dx, and that is helpful because this turns into root over y into dy, where 1 plus x square got to y and 2x dx was written as dy. And this is an easy one because this is just y to the power half dy, and using the rule you can find it as y to the power half plus 1 divided by half plus 1 plus c, which is basically y to the power 3 by 2 into 2 by 3 plus c, which is the answer, right? So this is the integral and this is the answer, and we can just substitute back to get our answer in terms of x, obviously. So it is basically 2 into 1 plus x square to the power 3 by 2 whole by 3 plus c. This is our integral, right? So this type of integrals can be solved, but you need to be a bit cautious about them. So let us do another one. Evaluate dx. So we want to evaluate 4x by root over of 2x square plus 1 dx. Again, it should be noted that ddx of 2x square plus 1 is equals to ddx of 2x square plus ddx of 1, right? And ddx of 2x square is just 2 into 2x, and ddx of 1 is 0, which gives you 4x. So you see that 4x is already present. The derivative of the term of 2x square plus 1 is already present. And if that is so, what we can do is we can substitute y equals to 2x square plus 1, and thus we see that dy is equals to 4x dx, and this would turn our integral into something like this. But this just only means that it's y to the power minus half dy, and using the rule we can write it as minus half plus 1 by minus half plus 1 plus c, which is basically y to the power half, and this becomes 2 because it's a half in the denominator. And we can substitute back our answer to find it's just 2 into root over 2x square plus 1 plus c. If you differentiate this using the chain rule, you would find that the answer is basically 4x in divided by root over 2x square plus 1, which is amazing because differentiating something is very easy while integrating something is insanely hard, just because of the methods or the ways you have to look for, right? Okay, let's do another one. Evaluate sine of root x by root x dx. Now again in this one, as you can see, the only portion that is not going with the integral is the root x inside the sine, right? And we are kind of sure that whatever else is present in the integral should be the derivative of that, right? So let's see. We observe ddx of root x is just equal to ddx of x to the power 1 by 2. Now we have learned previously that the ddx of x to the power something is just the coefficient comes out, so the coefficient comes out, and the coefficient the power comes out as a coefficient, and the power is reduced by 1, which means it is half into x to the power minus half, or in other words 1 by 2 root x, right? So if we were to differentiate, what we would get is something like this. Let y equals to root x, then dy should be equals to dx by 2 root x, right? But we see dx by root x is also present, so what we get from this equation is dx by root x should be equals to 2 dy, and we can put this, we can absolutely put this to get the integral as for I equals to sine of y, because root x is y, into 2 dy. Since 2 is a constant and is in multiplication with the rest of the integral, it comes out, and we only have to integrate sine y dy, which is just minus cos y. So it's minus 2 cos y plus c, and putting the value of y back, what we get is minus 2 cosine of root x plus c. This is the answer, right? So you see, like, this kind of integrals can be solved, but then again we have to be a bit cautious. So let us solve a lot more problems. Example 7. I will try to do this as much as I can so that you get the idea of method of substitution completely. And if you have any trouble in evaluating derivatives, please go back to the last videos to find out how to evaluate a certain derivative or how to do complex derivatives as well. Okay, so example 7, evaluate integral of 2x e to the power x square minus 5 dx. So let us denote the integral by I, so that I is equals to 2x into e to the power x square minus 5 dx. Note that now again in this integral we are trying to see that since the derivative of x square minus 5 is just 2x, what we can do is y equals to x square minus 5, which should give us dy is equals to 2x dx, right? Then on substituting, I is equal to e to the power y, and the 2x dx becomes dy, right? And you know the integration of e to the power y is just e to the power y plus c, and you put in the value which was x square minus 5 plus c. So this type of integrals, if you find the derivative of a term directly present inside the integral, try to substitute for that term so that you can reduce it into a common integral or an integral that you know of, okay? Because only then would it be easier for you to find out what to do. So we will continue our examples, but first let us learn one more thing. Let us do one more example, then from the next video we shall also do all the other indefinite integrals that we are required to do in the method of substitution, but also we will do some of the definite integrals, and we will learn how to do the definite integrals as well. So let us do this. This would be example 8, right? Yeah. So we'll continue from example 9 in the next video. So this would be the last example for this video. So let us do this problem where we have integral of cosine of x dx by 1 plus sine x. So this one looks a bit more tedious than before, but note that ddx of sine x is just cos x, right? So as we can see, cos x dx is present in the numerator and 1 plus sine x is in the denominator. So if derivative of sine x is cos x, then derivative of 1 plus sine x should also be cos x, right? So rather than going for the substitution y equals to sine x, what we can do is we can directly go for the substitution 1 plus sine x, then let y equals to 1 plus sine x, and from that we get dy is equals to cosine of x dx. This would give us our integral as y equals to integral of dy divided by y, which is just the integral. This integral is evaluated as a natural logarithm, right? So ln of y plus c, and remember the y is always positive, so it's rather a modulus. So the answer by putting back the value of y would be ln of 1 plus sine x plus c, which is the answer. So these are by far right now the easier parts of the integral, but we shall do some more integrals to find out how to do them, and then we shall move on to the next part where we learn how to do methods, integration by substitution, and some other methods for evaluating indefinite integrals, such as, let's say, the surds and the radicals. And finally we can move on to definite integrals, which are of utmost importance, which is why you are learning indefinite integrals, right? Okay, so we shall meet in the next video. For now, please do practice whatever has been taught, because a lot of examples have been taught here. And for the related theory, please download the Bretter's math app and watch the videos right in there, and also you can see the theory side by side. The link is in the description. Thank you.